Okay, so welcome to this week's Origins Colloquium. It's a pleasure to introduce Devesh Nandal, who's just arrived in Virginia. Devesh did his bachelor's degree in engineering in Leeds in England, then did worked in industry for a few years, biotech, as I understand it. Did a master's degree at KTH Stockholm with visit to ETH in Zurich, and then started a PhD at Geneva Observatory, where he just graduated a few months ago. And during his PhD, he's worked a lot on stellar evolution, Geneva Stellar Evolution Code. We'll hear, I think, a lot about that now in his talk, but with a focus on understanding what's going on in the most massive stars in the very early years. And now at Virginia, he's a Beta Origins postdoc. So welcome, Devesh. We look forward to your talk.
Thank you very much for the introduction. So yeah, hi everyone, I am Devesh, and as Jonathan said, I did my PhD in Geneva under Professor George Manet, and the work I'm going to present was mainly done during this PhD. So I will talk about the massive stars in the universe, and I'll leave that with a big asterisk because you'll see that the range of masses will change from reasonable to quite absurd. And the processes that I'm interested in mainly that I'll talk about would be accretion, rotation, and dark matter interactions in such stars. So I'll begin this by giving you a little roadmap of what's to come. So the first thing I'll talk about would be the massive stars in the current universe. So these stars are at and around solar metallicity. The phenomenon I'm interested in there would be rotation, and some parts will be about mass loss here as well. Then I'll move on to the early universe, really, or to these population III stars. Here, the main focus would be on the formation, the growth of these stars, that is accretion, of course, and the internal structure of these stars, how it changes and is quite different, and a little bit about rotation at the end as well. And finally, I'll talk about these fabled supermassive stars and how their evolution is absolutely quite fundamentally different from these normal population III stars. The way they end their lifetime is also quite different. And then we'll even complicate the situation more in terms of physics and interesting things, where we'll talk about the POP 3.1 model by Professor Tan and others. So this is really the roadmap. And throughout the talk, I'll really focus on the major findings from my research. So I'll leave all of you to ask me all the interesting questions at the end. So before I begin with the work itself, I'll quickly introduce the Geneva Stellar Evolution Code. And it's really a 1D stellar evolution code, which is mainly used to compute massive star evolution. It's very much like the Mesa code that you're all familiar with, that Professor Aris is right there on Zoom, I see. And what it simply does is it solves these equations of stellar structure. And along with that, we take into account the equation of state, where we include the contribution from gas and radiation. We also assume partial ionization in the outer layers. Of course, it has to have nuclear reaction rates, so all the reaction channels you can hope for. There are about 55 isotopes in this Geneva Stellar Evolution Code. Opacities are all calibrated on the sun. We use them through tables. The most common one would be the one from the Opal group. Convection is treated via different criteria, so the Schwarzschild criteria, the Ledoux criteria, and to take a complex process as convection, a 3D process into 1D, we use this mixing length theory. And what it really does, again, to quickly summarize what's happening in the code, you construct a series of neighboring models. You assume this cellular rotation in the star and the structure of a star in general being made of these concentric shells. At each shell, you're solving for mass, radius, temperature, density, luminosity, abundances. It's all put into a matrix. You diagonalize the matrix. It's like a shooting method. And then you evolve this to get the next set of converged models. If you find convergence, if you don't, you play with the time steps and so on and so forth. So really a very classical way to do it. And Mesa does this quite popularly. So Geneva does the same. And what's Geneva really known for in the past, my big predecessors like André Médère and George Manet have worked on the rotation aspect in these massive stars. That's what the code was known for. And the first work I did was really to build on their legacy, was to study the impact of these rotational prescriptions in these massive stars, right? So the contribution of rotation in a star is twofold. The main one being it transports the chemical species from the interior to the outside. And the other one is a transport of angular momentum as well. It's done in a very simplistic way I'm showing here. So the transport of chemical species is by that equation over there. And the main coefficient that we were going to talk about here will be the shear coefficient and this dF, which really boils down to this DH coefficient. This parameter here is actually for the magnetic models, and I wouldn't be talking about them here, but if you have questions, I'd love to discuss this. So this is the internal magnetic fields part. So the first work was really to study the impact of changing these rotational prescriptions in these massive stars. So to give you an example of some of these prescriptions, here are the papers that I've listed here. And the goal was to study the evolution of two types of solar-like massive stars, a 15 solar mass star that forms a type 2p supernova at the end, or a 60 solar mass star, which is, let's say, the upper mass limit, and it's really where you start to see mass loss being dominant in such stars. So these were the two models I studied where I changed these prescriptions to see how the evolution is affected. So quite a tedious paper. This one was about 18 pages, so I'm really going to show very small parts of it. A lot of like inner workings of the code and to see how physics affects evolution. So here is some tracks for the 15 solar mass model. What you're looking here are the profiles of different diffusion coefficients. The prefix here is this d shear coefficient, right? The suffix here would be the dh. So I'm varying these coefficients, and you can see in the profiles of some of them, they are quite different. And what this really means, this was at halfway during the core hydrogen burning stage of the model, and it changes quite a lot of things, as it turns out. Changing these prescriptions can change how the star evolves. You can see all these tracks, this signature hook, as we call it, is the end of the main sequence. You see some tracks are more luminous, some are less luminous, some are hotter, some are not so hotter, some have more homogeneous mixing. So all these effects are of changing these rotational prescriptions. Also, the size of the convective core is affected quite a lot depending on which prescription you apply. And then the kind of profile of hydrogen that you see at the border of the convective core changes a lot depending on which prescription you choose. Also, the distribution of the angular velocity inside the star could also vary depending on which prescription you use. So like I said, very tedious work trying to understand really how the physics work. And you might be wondering, what's the point in all of this? Why would anyone outside care? So I'll show you the next work we had a chance to do. But to quickly sum up what this work, one-line message of this work was, it's important to consider rotation in stars, but it's not just important to think of rotation, it's to think of how you implement the rotation, because the evolution could be quite different. And it was apparent in this work here on Betelgeuse. So by the time we were finishing this paper, Professor Hideyuki Saya, who's had maybe 5 decades of work in doing pulsational analysis, he approached us and he wanted to look at the star Betelgeuse. As it turns out, I'm sure we're all aware, it went through this dimming phase, and people were wondering what's going on with the evolution. Most people in the literature would agree that the star is at the end of its lifetime, so around core helium burning stage, a few 100,000 years left before the star goes supernova. And there were a lot of these measurements of these different pulsational modes, these periods that were observed in Alpha Ori Betelgeuse. And our goal was to figure out a stellar evolution model that can not only fit these periods, but also reproduce the position in the HR diagram, so the effective temperature, luminosity, the radius, and also some surface abundances. So this is exactly what we try to attempt. We find a couple of models around 19 solar mass with a given rotation rate that could not only fit these, like I said, these periods, but also the position in the HR diagram. This is all well and good, but the very interesting part, why we were very controversial and we had an interesting time with everyone else who disagreed with us, that if we match all these physical properties, as it turns out, Betelgeuse is not in core helium burning, but it's in the middle of core carbon burning. So what that means for all of us here is that it could explode anywhere from tomorrow or in the next 100 years or so. So this was a study that got a lot of interest, and it's really due to understanding all these internal. So this is a plot that really shows that time before collapse, and it's around here. This is the carbon burning, so very little time left. So yeah, so this is really just to show how rotation, once you get the recipes right, as it were, you can apply it to real life scenarios. And now we move on to the massive stars. Really, this is where I might start to lose you with the numbers that I'm going to throw at you. So the goal is now to look at these population III stars, these metal-free stars in the early universe. And the work we were very interested in was work by John Reagan. So he did these 3D zoom-in hydrodynamical simulations of star-forming regions, where this halo that I'm showing here in picture, this is halo A. And in this halo, he subjected this halo to Lyman-Werner field. As it turns out, if you subject this to Lyman-Werner field, you suppress the formation of molecular hydrogen. The temperature of the gas can rise, and it can go up to a few thousand Kelvin, where it can collapse monolithically. So what he saw in his simulations, that if you expose this halo to this Lyman-Werner field, the mass of the star that you can create can get something as large as 6,000 solar mass shown there. Whereas the one that's not shown in the picture here, halo B, the most massive star you could form there would be around 173 solar masses in this case. So our goal in terms of understanding the physics, the stellar evolution, was to take the accretion history of all these stars that you see are being formed here and to do some stellar evolution calculations with it. And the focus there was to determine this critical accretion rate. Now, this critical accretion rate, simply put, is the accretion rate above which a star can evolve as a red supergiant protostar. A star is nicely bloated all along the Hayashi line, and you can bypass all these feedback and other issues that you have with ionizing photon production. All these could be suppressed if you have a star that's all the way sitting on the right side of the HR diagram. But what it truly means to be a critical accretion rate, it could be understood by when the accretion timescale of a star is balanced by this contraction timescale of a star. That's what a critical accretion rate is. And it's very useful for people doing large-scale simulations where they want to form much, much larger supermassive black hole seeds. How do you get to those masses? Well, you need to keep the star bloated and big. So that was the goal. And on the left here, I'm showing, of course, a very classical stellar evolution plot, just an HR diagram once again. And the points from 1 to 5 are all the pre-main sequence evolution. So that's the track you normally don't see. And the part after that, you see all these 10 tracks. I followed the evolution until the end of core helium burning. The mass ranges that I chose were from the simulations, and they were chosen because they were quite interesting. The accretion rates would vary because this is a realistic hydrodynamical simulation, not a constant accretion rate, what we normally assume in stellar evolution. So models ranging from mass from almost 500 solar mass up to 6,000. And there's some interesting things that happen in this track, and I'll just show one quick detail, is if you look at point 4 over there are a couple of tracks, actually most of them, who form this loop-like feature here, where there are 2 other tracks here who climb vertically along the HR diagram. This is this Hayashi line that we spoke of, by the way, right? The one that keeps the star bloated. So the question was, what's causing these stars to do that? So we simply did a lot of tests, and here I'm just going to show you one such test where I took a model, one of them that went all the way up here, and the other one that is from this loop. I plotted them here, and we indeed were able to determine a critical accretion rate of 2.5 10 to minus 2 solar masses per year. So if you exceed this rate, you'll keep your star nicely tucked up on the Hayashi line, along the Hayashi line. And if you go below that, you'll have a more compressed, contracted, bluer star. So this is what's really shown in this work that we published. So you have an accreting protostar after the first 100 years of evolution or so. Once you pass this luminosity wave episode, I'd be happy to answer what that does mean, but I'm not going to get into it. So anytime you exceed the accretion rate above the critical limit, you have a red supergiant star, and if you go below it, you have a blue. If you go into hydrogen burning, we found another critical accretion rate that's a bit lower. We can also talk about that. So then the idea was really to develop these POP3 models that come from these hydrodynamical simulations. But once again, what's the point of this? Because if it's just a stellar evolution calculation, I can throw numbers at you. Is this realistic? Can the universe form objects such as these? So that was the next target that we had, because as we were finishing up this work, JWST started giving out wonderful results, and one such or 2 such results I'm going to talk about are these galaxies at high redshift, right? The 10.6 and the 8 point something. So this is GNZ11. There's also Sears 1019, where these galaxies showed unusually high nitrogen over oxygen ratios. So in this case for GNZ11, this ratio was about 4 times over the solar ratio. And the question is, what's creating all of this ratio? What kind of star formation is producing this really strong signature of nitrogen? And people really jumped onto this idea, and there were wonderful works that were published before. So this is just some of the works I'm highlighting. The scenarios that they talked about were something more, let's say, not so something more standard in a way, where you could have winds from Wolf-Rayet stars, maybe AGB stars are the ones that are polluting the ISM, to something more complicated where you could have runaway collisions and you can start to create these more massive stars. So our goal was like, hey, we have those models from John Reagan's work where we have these variable accretion rate, these supermassive stars with these funny masses of 6,000, 8,000 solar mass or so. Can they do the job here in this case? So that's exactly the scenario we propose. And if you can ignore the mass for a minute, the scenario is quite simple. All you do is you normally accrete your star during the pre-main sequence, you evolve the star, and since these are POP3 stars, there's very little mass loss in them. At the end of the lifetime, they collapse and form this black hole, and this black hole eventually accretes, all right? Nothing special happening here. So can this scenario really make sense in this context? So I'm going to show you two plots here. On the right here, we'll focus on this Kippenhahn diagram. So here you see an almost 9,000 solar mass star. So if we look up until 1.5 million years or so, this is the Kippenhahn diagram, the evolution of radius versus time in million years. Up until here, really, dare I say, isn't this more likely a classical massive star, right? A convective core, a radiative envelope. There's hydrogen burning occurring here. But as the evolution proceeds further, as you get into core helium burning stage, the structure changes significantly. And the plot really doesn't do justice here because there are a lot of these intermediate convective zones that start to form. So the structure becomes from convective core, radiative envelope, to almost 80 to 90% the star is convective. What that really means is if you look at the abundance profile at the end of core helium burning, you see, of course, helium, the surface being strongly enriched in helium. Well, that's because hydrogen is being converted to that. So that's hydrogen on the surface here. But this was our light bulb moment where we saw that actually nitrogen is the element that's strongly enriched at the surface. So we explore this a little bit further. But to give you an idea of what really happens in a star such as this, so this is this star during its core helium burning stage. This central part here is the helium core, the convective helium core. It's surrounded by this thin, it's hard to see here, hydrogen burning shell. This is also convective, followed by another convective zone. And this is where these intermediate small dotted convective zones also come into play. And then there is really outermost convective zone. So what I'm trying to say is it's largely convective. So what's happened by the virtue of stellar evolution, really, you start to fuse helium in the core during core helium burning stage, you produce carbon. And because the core is convective and the layer above that, the H burning shell is also convective, you can efficiently transport this carbon to the hydrogen burning shell. And once you do that, this carbon is then producing the nitrogen, which can then be enriched to the surface simply by the process of convection. So I should say there's no rotation in play here. This is simply the convective nature of star that is allowing the transports to occur from the core to the surface. So then we took the same attempt like we spoke of. So again, it's quite a busy plot and there's a lot going on here. I'd like you to just focus on the top part here. So the N over O ratio was to the O over H ratio. The Sears 1019 object is right here, and GNZ11 is right here. These are the less conservative estimates that are shown here. And the result we found was that if we take these individual stellar models whose mass is above, let's say, 1900 solar masses or so, and below 9,000 solar masses or so, we can really sit nicely in this place where we are close to these abundances. But not only that, if we take all the stars from this simulation of John Reagan that we showed in the very early time, those little dots, we take all hundreds of those stars and we add some standard massive stars to the mix and see what kind of chemical enrichment will these stars do, we find that actually the entire halo with these massive stars can reproduce these results quite closely. And not only for the nitrogen over oxygen, but also for the carbon over oxygen. That's another measurement that people were wondering where it's coming from. But are these results robust? Well, like I said, there are other scenarios people have proposed here. And we also took another turn at this scenario. So now that the crazier objects are explaining this, what about the normal population 3 stars, right? A standard 9 to 120 solar mass star. Can it do the job? And the answer was no. If it's just normally rotating, we saw in this work, we were not able to reproduce the ratio. However, if we go by the idea that POP3 stars are fast rotating, and there's work done in literature, there's a lot of work where it shows that these POP3 stars would be rotating fast due to this omega gamma limit, then by fast, I should say it's about 0.7 of the critical velocity. So critical velocity at which you have mechanical mass loss. So it's almost getting there. So these objects can also reproduce these results. So this was our, if we are one of the many people, then this shows that maybe this is the first sign of not only these population 3 stars in the early universe, but maybe population 3 massive stars in the mass range of thousands and above. So there's that. Okay, and then I'll move on to the super and the supermassive stars, as I would say, right? So if I haven't lost you by now already, I'll definitely lose you now. But I can promise you we can talk about the physics of formation of these stars, why we think they form, and what's the reason behind them. So this work really sums up most of the things I did during my PhD. These are tracks of POP3 stars from the pre-main sequence, so right from when they're a seed of a few solar masses all the way till the end of their evolution. And some of these numbers should be very alarming to you because look at that luminosity. This is not a galaxy or anything. That's a single object. That's a single star. And the accretion rate varies from something reasonable to 10 to minus 6 solar mass per year, all the way up to 10 to 3 solar masses per year. So if you're wondering how can a single object have this much accretion rate, we can talk about it. But the supermassive stars that I'd like to focus on are around this region here. So the accretion rate higher than 10 to minus 2 solar mass per year, which if you remember is quite close to that critical value we found. So these are the stars that we're interested in, and the way they end their life is quite interesting, and we'll talk about this aspect. So again, there's a lot of physics to talk about how their structure is different, but I'm going to focus on just one big aspect of this, and this is how they end their lifetime. The final fate of these stars, these supermassive stars, is quite unique. Actually, there's a definition we'll get to about supermassive stars, hopefully by the end of this. So the work we did there was simple. We performed this linear adiabatic radial pulsational analysis. It's quite a mouthful, but the idea simply is you put a test charge inside your stellar evolution structure, somewhere inside the star. You perturb the equation of the stellar structure, and you see how this mass behaves. If it leads to pulsations that grow exponentially, that means the structure is unstable, and there should at least be some mass loss, if not some even bigger disruption. So from this equation, what we're really interested in is this quantity here. If this value is negative, that means the structure is unstable. If it's positive, that means the pulsations were there, but the structure was able to recover, and the star will continue to live. So those crazy accretion rates that I showed you, and I haven't even told you what their masses are yet. So we looked at an accretion rate, a net average accretion rate of 10 to minus 2 solar mass per year. And we found that throughout its lifetime, this structure was stable to these pulsations, to these instabilities. So here is the mass. Here you're looking at the growth rate. Anything below 0 is stable, and anything above that, which means the instability is now growing. So this track was nicely sitting in a stable place. But as you increase the accretion rate at 0.05 solar mass per year, you start to see these tracks reach this unstable territory. So what this really means is if we look inside the structure of one such tracks, by the way, please don't read into this number because there's a secret or like a reveal that's going to come in a minute. If we take the 10 solar mass per year track, you see the amplitude of pulsation, that's what I'm plotting here, really is occurring in the stellar interior, really in the core of the star. What this means is that once this instability is reached, the collapse of the star will occur at a freefall timescale. So this instability will force the core to collapse, and then the rest of the star will follow up. And this, to me, is the real definition of what a supermassive star is. A star that undergoes this direct collapse. And the minimum mass you need for such a star, we found out, was 80,000 solar masses. So if you exceed this mass number, general relativistic instability will come into play because these stars are very much radiation dominated, and it forces the star to collapse prematurely. And we think it leaves no transient, but we'd love to talk to people about how maybe it doesn't.
Sorry, is this a GR instability?
This is the GR instability, exactly, yeah. So this is just one instability. There are other instabilities like pulsational instabilities that I will not talk about.
You started with the pulsational instability.
Yeah, so GR instability is a pulsational, but it's not the pair pulsational instability. Sorry, that's what I was trying to get at. Yes, yeah, absolutely, yeah. So, and this really is a plot that once again encompasses a lot of things. I always show this is a very simple plot, and it'll be very boring plot. It has a lot of bells and whistles, but it's quite simple. All you're looking at here is the maximum attainable mass as a function of accretion rate. And this plot, this gold line here, is the track of these POP3 stars. And nothing special here, right? The slope until here is quite normal. If you want to make your light black hole seeds, your neutron stars, your core-collapsed supernovae, this is the accretion rate you need. If you're after your intermediate mass black hole, you increase this net average accretion rate and you'll fall in this range. But at some point, you see the slope of this starts to change. And this is where this general relativistic instability kicks in. So you start to see that these numbers are appearing. What these numbers really mean, this shows the central mass fraction of hydrogen inside the star at the time of the instability. So all these stars before that, they live their lives as normal stars, right? They go through all the evolutionary stages, they burn the nuclear fuel like they're supposed to, and at the end of their lifetime, they'll collapse. But if you go to these higher masses, above 80,000 solar masses or so, or for instance, in the case of 0.1 solar mass per year, you see the instability sets in already in hydrogen burning. And as you increase the accretion rate, this instability starts to set in earlier and earlier. So the question is very simple. You know, if we think that the definition of a star is something that burns nuclear fuel in its center, and if you keep on increasing the accretion rate, we get to a territory where the star hasn't even begun to burn in nuclear fuel. It's still very much a protostar, and it collapses under its own weight due to GR instability. So is there a theoretical upper mass limit that we spoke of for these stars. And I think if you follow GR instability, even if hypothetically you have all the mass in the world available to accrete onto a single object, you can forget about the radiative feedback and other issues. Hypothetically, if you can throw in all the matter at a star, how large can it grow? Well, GR instability sets a limit, which is about 800,000 solar mass. That's when I'm sure I've totally lost you, but so there's a lot to talk about here. There's another line here which shows dependence on metallicity, and also adding dark matter to this could also affect situations quite a lot. So this was the end of this part here. Now I'm going to talk about the work that I've been doing with Professor Tan, and it's to look at these very interesting objects, these dark stars, right? And the idea, I will try not to butcher it because I have the expert sitting here. Imagine in these early halos, these mini halos, you have a lot of matter falling into these stars. We've shown the accretion rates could be quite large. The baryons are falling into a gravitational well. If as we know, there's also a lot of dark matter density around these halos, and if this dark matter could also start to seep inside the star simply due to gravity, it will start to accumulate in the center of a star. And if this dark matter happens to be WIMP, then it'll do certain interaction, it'll start to annihilate, and it'll create an energy source that is independent of the nuclear energy. So essentially what this means for stellar evolution is you're adding another epsilon, an energy term inside the star. So this is one of the models we implemented. This was done by Marco Taozzo, where the number of WIMPs in a star are given by this capture rate, the self-capture rate. We can talk about the details, annihilation rate and evaporation rate. So the question was, now if these WIMPs are indeed these dark matter candidates, and if we can, logically, we should be having these WIMPs in these early POP3 stars in the early universe, seeping into these stars, these normal baryonic stars. How would the evolution be different? Do they have different chemical signatures? Are they different from normal stars? So there's two projects we're now working on. And the first one is simply the dark matter annihilation in reasonable mass POP3 stars, right? These are the POP3-2 candidates, actually, as Professor Tan has shown. So this is a 20 solar mass star. And to really give you a very quick overview of what's going on here, these are simply non-rotating models. And the fiducial model here is just this black line here. This is a model without WIMPs. But like I said, as you add this WIMP annihilation into a star, you start to see this is the beginning of the zero-age main sequence. It starts to shift at lower and lower effective temperature, meaning the star doesn't have to really get hot enough. The WIMPs are already helping the star support against gravity, so hydrogen burning can occur at much lower temperatures. And then this is just for the non-rotating cases. For rotation, things get even more interesting. So not only do the start of the main sequence is effective, you see this is the end of the main sequence. Again, this is the fiducial model, that as you increase this WIMP density inside the star, you start to see the track shift. Not only the effective temperature is changed, also the luminosity is changed. So the stars are behaving as if they are like almost a solid body. They're rotating like that. And this leads to a lot of interesting chemical enrichment at the surface. So this is a work, we have these models right now, and this is a paper we're writing on these POP 3.2 cases. And then going back to my favorite crazy big numbers, also in these POP 3.1 models, right? These supermassive stars, these accreting supermassive star models. Here, once again, I have an HR diagram to show you. This is just a Zam's line to give you an idea. This track here, you see the wiggly one, is just a normal POP3 star that you saw earlier, one powered by baryons. And the next one here is a one powered by WIMPs. So a lot of interesting things are happening here. And first, you can see where this object is ending its lifetime. It's ending its lifetime here. This baryonic star has a final mass of around 30,000 solar masses or so. Its age is about a few million years. Whereas the star that you see here that is powered by WIMPs reaches a much higher luminosity. And this star's final mass is around 490,000 solar masses or so. So given the accretion rate is same, just by adding WIMPs to it, it allows you to extend the lifetime of the star. And by the way, this WIMP-powered star, in this case, the dark matter density is so high, it's not really burning any hydrogen. It tries to burn a bit of hydrogen here, but then the WIMP density reaches a critical point where the annihilation is enough to sustain the star. So this guy is a protostar by definition. It's not burning any hydrogen. But we see that still this general relativistic instability forces the star to collapse at a mass of, 490,000 solar masses or so. So still there's an upper limit. Here, by the way, I'm also showing this ionizing photon flux here, for instance. And that's a better way to talk about this. So again, it's ionizing photon flux versus mass, and this is the effective temperature. So these, if these stars are out there, these POP 3.1 candidates, they will look quite interestingly very different. And even if they will collapse due to GR instability, and if there are even some pulsations before this collapse, the chemical signature of this star would also be different. So not only do we have a better chance of observing them because they live much longer, they don't live for a few million years, but they also would have a different chemical signatures, we hope. But all of this work is something we're continuing to do. So these are the two papers we hope to get out before the end of this year. And of course, it has different implications on the supermassive black hole seeds, but I think I don't want to go overboard. I'll quickly sum up the things I talked about here. So really, first part was about the impact of rotation on the stellar structure for the stars in the current universe. Then we saw how accretion takes an important place when you're growing the stars and how it affects the structure. We talked about population III stars. We also looked for the chemical signatures of these POP3 stars. Can they exist? I haven't told you about this very interesting candidate called GS3073, if you've heard about this. There are newer and newer galaxies that are coming out that are absolutely so complicated to explain that the work that I showed you previously, for instance, the GNZ11, the CIS 1019, other people can explain it, but this galaxy, absolutely no one can except for us with our model. So there's some very cool things happening in this field. And then this GR instability and how it leads to supermassive star, what their definition is, in my opinion, and what the maximum mass is. And then these newer models for dark stars, the POP 3.1 and POP 3.2. The things I didn't get to speak about, which I'd love to talk about, are the internal magnetic fields, the calibrated Taylor-Short dynamo, and how it affects the evolution of a star. The advanced nuclear burning stages of these POP3 stars. So when they reach core silicon burning and all these advanced evolutionary stages, how do they look different? How does the chemical structure change? Rotation in also these stars. For the first time, we're now able to rotate these absolute monsters of 1,000 and 5,000 solar masses. So this affects the evolution quite differently. And finally, people also say that these stars can grow by collisions. So how does the structure change from a star that is undergoing collision versus accretion? We also have some preliminary results on that. And with that, I'll shut up and thank you very much for listening.
Great, thank you. Okay, so we have plenty of time for questions and discussion. Raise hands here in the room. I think at Chalmers there's another event, so that it's not a physical room at Chalmers today. If you're online, just raise your hands there and I'll take your question. Any questions for Devesh then? So Ryan first.
Yeah, so I'm just regarding the chemical signatures bullet here, how your model can reproduce that one galaxy, but other models can also reproduce that specific galaxy.
Yes.
So that's probably fitting like photometry GWST data. I think with like near spec or MIRI, or you'd be able to further point to your model, or do we need new instruments maybe to tailor those specific galaxies?
These abundance must be done from spectra, right?
Yeah.
Yes.
Okay.
Yeah, they are. But the exact spectra of the star itself, there's not many models out there for this mass range to infer what's going on here. But yeah, I think what we have with JWST now, if we look for more of these candidates, I think we can quite easily pinpoint on what a POP3 signature would be. Because the part that I didn't speak about is this another paper we're writing, where if you have a POP3 star versus a slightly metal-enriched star, the CNO cycle is quite different. So the surface enrichment, the signature of a POP3 star is very different. And I think all of that could be picked up by...
But these are nebular abundances from spectra in the galaxy, the ISM of the galaxy. How many galaxies have been measured? And are these just the outliers of a population that's more normal?
Yeah, exactly. Most of them don't have such high N over O, but there's an increasing number. I think I can count about 4 or 5. There's UHZ1 as well, which has an abnormally large black hole, but also very high N over O. And then this GS3073, which is actually at a redshift of, I think, 6 or so. So it's not that crazy. It's not a 10. And it's much more reliable result. And there the N over O ratio is here. So when you get to that galaxy, all the models that I showed you before, what people are talking about, the Wolf-Rayet, the AGVs, and the runaway collisions, none of them can reproduce the ratios. And as you can see, our individual stellar models set up there.
Well, I have other questions on this, explaining these ratios. But let's go to...
Yeah, so you mentioned these WIMP-powered stars and how they're definitionally protostars. Is there any reason we wouldn't expect them to have some hydrogen-burning shell involved?
Oh, so sorry, yeah. You're absolutely right. So The ones I showed you, the big guy, that is a protostar, right? This one here is a protostar, but these other guys that you're looking at, I'm sorry, I should have mentioned that, they are very much completing their evolution, right? They are finishing their main sequence. So not only can you have a hydrogen burning shell, which comes during helium burning, but they will do the general evolution. The simple caveat here is how much of dark matter density do you assume inside your star? As you increase it, if you reach this critical value, then WIMPs will tell the nuclear reaction to just sit back and they'll take over until all the WIMPs are depleted. But if you add a little bit of WIMPs and most of it is your nuclear fuel, then that'll be interesting. And actually, that's what we're trying to do here, to see that if there's a little bit of WIMPs, how does the structure change? And you can see, right, that they are burning hydrogen, and they, of course, go on to helium burning, where you have a hydrogen shell and other things.
Okay, other questions? Yes.
This is, I feel like so much fun listening to this talk. I'm also, now I know who made our whiteboard look very pretty. So this is really cool. One thing I'm trying to wrap my head around is, in these early stages with these extreme stars, protostars, what's the environment like for less extreme stars, right? So is there a sense of like what an IMF would look like? Are smaller stars, even like stars that we would consider massive, but just puny compared to these, like what are these things even able to form? Are we ever going to observationally detect them? Like, what's the situation?
Right. So again, they're competing models. And if I go back to this atomically cooled halo idea, right, where you don't have molecular hydrogen, but atomic hydrogen, there people have shown out different results. Generally, when you form a massive star of even a few thousand solar masses, that is the one that's really eating up all the matter. Even if you do have some star formation nearby, people also are showing from their 3D simulation that very quickly in the pre-main sequence already, these stars are just sucked in by this massive object. So if you see a star this massive, then it usually should be, on its own. But this ACH is a very, already the people who propose this theory say that it's a very, not everything out there in early universe is ACH. It's extremely unlikely. There's very, very, very few cases. And this is a very specialized way where you can have just
well, related to this is then the chemical signatures that come from the IMF. So perhaps if you go back to the nitrogen, and when you're trying to explain GNZ11, do you need all the stars to be these supermassive stars? Or
so,
I know you did the Reagan IMF, and then you could just make it there, but you needed the whole of GNZ11 to be this atomically cooled halo, did you?
Oh no, sorry, no. So we don't really. The only thing I take from Reagan are these variable accretion rates. So now I can tell you, if I forget about the variable accretion history and I just take a constant accretion rate, I can still reproduce this value. So the atomically cooled halos don't really impact this, right? The point is, what we look at is what is the mass range of a star needed to produce this kind of a chemical signature, and it's independent of whether they're formed in atomically cooled halos or not. The point was that it's more realistic to have models that have a variable accretion rate. So we took the models from Reagan. And about the IMF, if I may, no one knows what the IMF is, right? So one of the things could be that using these models, we can now extend the IMF. So how many stars do we need to produce a ratio? Just one, or two, essentially. So in the works of John Reagan, there's one 6,000 solar mass star forming and one 4,000.
But hang on, to make the absolute abundance of metals that are seen in GNZ11,
yes,
surely
you need other stellar so sorry,
the population of stars.
Absolutely. So the idea is simple, that you start off with a completely pop-3 environment. In this first star forming time, you form these supermassive stars. They die, they start to enrich the ISM, and then the subsequent stellar populations are formed, which bring down this N over O ratio to a lower value. So there's
effectively, you're constraining the IMF from this abundance ratio somehow.
Yes, that would be the idea for future work. Yes, exactly.
All right. Any other questions for Devesh?
So where does the Lyman-Werner field come from in Reagan simulations?
I think you're going to need to repeat the question for people online.
Yeah, he says, where does the Lyman-Werner radiation field come from? I must say I am not so well versed on this. I think he forms these mini halos, and I think he's just exposing them to Lyman-Werner field. I don't know what the physics behind this is and why these are specifically. Why is a Lyman-Werner field? But there is like a plethora of literature that I am ignorant on. But
But it's very uncertain. I mean,
Yes.
they're just assuming there are other galaxies around or other sources of UV photons. It's either done self-consistently by them forming other stars in a cosmological volume, or it's a parameter
Yes.
applied to a given.
Yeah, you have a like influx of some UV photons. You assume a certain amount, which is what's causing this molecular hydrogen to be suppressed.
Asrian, please.
Of course, I want to ask about Betelgeuse.
Please.
The models that you showed, so do they include rotation?
They do include rotation, yes. So we
And
found
what did you assume? So there's been some controversy about whether Betelgeuse
absolutely.
rotates or not.
Yes, yeah,
So
I'm with you. So all these models, actually, so Betelgeuse, even if it's in core helium burning, right, the rotation severely drops off. The rotation rate drops off right after the main sequence. The value we get is around 5 kilometer per second, which is I think around the value that they say. Maybe it's 2 or 3 for Betelgeuse. It's unusually slow, right?
yeah, so there was an ALMA result where they had one epoch from ALMA and they found, that it was rotating rather fast.
Mhm.
But now there's been nice work by Yingzhe Ma at MPA that
Yes.
showed that you need more than one epoch to really confirm whether this is rotation. If you just take a convex cell, the thing that looks
Yes.
one cell going down, one cell coming up,
Yes.
so maybe it's not rotating.
So yeah, it mimics rotation.
So yeah, so I think the question of whether it's rotating, but would that change significantly then the result for your model?
I think
Still
all of
has to
these.
be carbon burning if you get rid of the rotation.
Yeah, yes, exactly. So we also try the non-rotating models as well. And yeah, we are a little bit off. What this is really parameter tuning, right? If we really go into the nitty-gritty, you choose like kind of the overshoots you apply, you choose what kind of mixing length you apply, and same with the rotation rate. So I'm sure there is a even more precise one out there that can, if you take 0 rotation and you assume, then you can get to a model. But it has to be found that almost all of the models are in carbon burning.
Even without rotation.
Even without rotation, yes, yeah. But without rotation, you see the star go a bit further away. They move a little bit on this side. So actually no star is gonna, no matter what rotation you take. So I tried models from all the way down from 14 solar mass up to 25 solar mass models. There's like hundreds of these at different rotation. And if I take non-rotating one, they sit over here. They can still almost get this right, the pulsations. But
I mean, there are some really low mass models. The range, Betelgeuse mass so on, that's
Mhm.
some as low as 9. But yeah, I haven't looked at it.
And I didn't mention, if I may, the other funny thing is there are these 4 periods observed, right? There's the 2,200 days, there's the 400 days, and the last 2 are 200 days each. The only thing that Professor Sayo came up with, this interesting idea, is that he assumed the longest period to be the radial fundamental mode, which is not what the other people say. And actually, a problem with this work was that the radius we're getting is a bit large. So the highest tolerance on the radius is about 1100 solar radii, and we get about 1186 solar radii. So we're still a bit outside the error bar on that, to just tell you a little bit.
I have a question about the rotation. So when
Please.
you put the rotation, is it the initial rotation or is it the current rotation? Because I think for at least MIST models, we can just set the initial rotation.
Yes, exactly. We start with an initial rotation. Yeah, we set a rotation at the ZAMs, and we can define it in many ways. So it's V over V crit, right? What is it with respect to the critical value? Yes, and then we let the.
So using the Geneva models, can we just use different rotation?
Absolutely.
Okay.
So that's what we do for this other work when I talk about GNZ11, where the fast rotating POP3 stars can do that. All the Stellar Evolution Code, MESA also, of course, is the big one. But yeah, absolutely, with GENEC, you can go to no rotation all the way up to quite high rotation. Rates, yeah.
At least for MIST models, when I get the isochrones, I cannot select the rotation. There's
I
just
see.
one, either it's
Yeah.
0 or is 0.4 for massive stars.
Yes, 0.4. So that's the standard one we take. But no, now there are tracks of 0.7 as well. And yeah, but it's one of those papers that has to be done. It's quite tedious, but it's very much feasible. It's an open project where you can pick different rotation rates.
But let's say, I mean, how well constrained is the modeling with and how you do the rotation in these 1D models. I mean, you showed some of the equations and prescriptions, but it sounds like there's some uncertainty in how rotation is treated and how it evolves and so on. If I don't know, if you had a whole population of stars born together, say in 30 Dorada star 136, and you model population, can you look at their HR diagram and just sort of say, well, there's a range of initial rotation rates, or is it degenerate with something else?
No, exactly. That's what they try to do. So first of all, the calibration of these prescription itself was done in 2012 in Sylvia Ekstrom's paper, so this prescription 11 with the D share from Medare and Halon and Zahn PH. So that's the one that's calibrated. But these other prescriptions that I showed, they are not really calibrated to anything. This is really like a more test of physics. And I think that's what they tried to do when they did this. They calibrated it to some of the objects. I'm not sure exactly, but the goal is really that you find some of these candidates out there that are well studied, maybe some luminous blue variables. You take different massive stars and you see is there a prescription where the track is really going through all these points. Yes, so.
Because from the formation point of view, nobody can really predict what the initial rotation, but if there's a way to back it out from this work, then it'd be very interesting. But so which models are favored then? Do people?
Well, for rotation, it's generally the prescription. I can show you the prescription number. So essentially, it'll be this Medare 97D share value and this Zahn DH value. This is the standard prescription they've used for most of the calibration. It's also calibrated to the sun. So this is the one that they use to explain the rotation of sun itself as well.
But how close to breakup are these things thought to be?
So this I choose on my own, right? So in this case, as Moshkin said, it's 0.4 of the crit, so quite far away from, they don't reach the breakup velocity. For this,
you can rule out non-rotating models.
Sorry, for which regards you mean? Like
in terms of being
explaining, yes, non-rotating models often produce much larger convective cores, and yes, they are, the tracks are quite, we can definitely say that you need rotating models for that. I think,
Great. Any other questions for Devesh? Anything online from people? Great. If not, let's thank Devesh again for a great talk.